Today's numerical is a simply supported beam 8 meter carries a uniformly distributed load of 3 kilonewton meter over entire span. Find the maximum bending stresses induced if the cross section is as shown in figure. This is simply supported beam. With uniformly distributed load 3 kilonewton per meter and cross section of this beam is this T section. So bending moment for this beam is WL square by 8. That means 3 into 8 meter span 8 square by 8. This 8 cancel. 24 kilonewton meter is bending moment. Now next find centroidal axis of this T beam. To finding centroidal axis of this T beam, use formula y bar is equal to a1y1 plus a2y2 upon a1 plus a2. Let us assume that this top flange part of this T beam is first part and this wave part of this T beam is second. That means A1 area of flange is 100 into 50, 100 mm into 50 mm. That means 5000 mm square. Y1 is centroidal distance of this top flange part from bottom part. From this bottom, this distance. That means this 125 plus 50 by 2. See, this distance is 125 plus half of this top flange part distance. 125 plus 50 by 2. For area calculation, we use multiply sign because rectangle area is B into T. That means width into breadth. And here distance from bottom. That means add distance. 125 plus 50 by 2 is 150 mm. Now next A2 web part area 125 into 50 mm. It means 6250 mm square. And Y2 is distance from this bottom fiber to mid of this web part. That means 125 by 2 is 62.5 mm. put this a1 y1 a2 y2 value in this y bar equation. Therefore y bar is equal to a1 is 5000 multiplied by y1 is 150 plus a2 is 6250 multiplied by y2 is 62.5 divided by a1 plus a2. a1 is 5000 plus a2 is 6250. So 101.39 mm is centroidal distance of this T-beam. So centroidal distance of this T-beam denoted as y bar is equal to this 101.39 mm. From bottom. Now next calculate moment of inertia for this T section. Moment of inertia about this axis denoted as I. So for this moment of inertia calculation, we have to use formula I is equal to I x1 plus I x2. Here I x1, that means this moment of inertia of flange part, and I x2, that means moment of inertia of this wave part. So calculate first this flange part moment of inertia is 100 into 50 cube by 12 plus area of that flange part 5000 into distance between this centroidal axis to centroid of this flange part. That means right here I is equal to BD cube by 12, 100 into 50 cube by 12 plus 5000 multiply by distance between this flange centroid to the centroid of this T beam. That means 125 plus 25. Here this much distance is 125 plus 25, that means 150 minus 101.39 mm. From this bottom fiber to centroid of this T, centroid of this top flange, distance is 125 plus 50, that means 150, and minus from this bottom to centroid of this T beam distance is 101.39. So right here 150 minus 101.39, and square of this plus this is ix1 term. Now next ixx2, ixx2, remove this Ixx2 is this wave part. Moment of inertia for only this wave part is 50 into 125 cube by 12. Plus this area of this wave is 6250 multiply by 125 by 2 is 62.5. That means 101.39 mm minus 62.5. Centroid of this wave part is here, something here, and from bottom distance is 125 by 2, that means 62.5, and distance from T section centroid to the only this wave part centroid, distance between both these centroids are 101.39 minus 62.5. And square of this. We use parallel axis theorem for getting this I section moment of inertia. So solve this one first. Ixx1 150 minus 101.39 square of this multiply by 5000 multiply by 100 into 50 cube divided by 12. This is 1.2306 into 10 raised to 13 plus the second part 101.39 minus 62.5 square of this multiply by 6250 multiply by 50 into 125 cube divided by 12 is 7.693 into 10 raised to 13. That means I is equal to 7.693 plus 1.2306 is 8.9236 into 10 raised to 13 mm raised to 4 is moment of inertia for that T section. Now next find main objective of solving this numerical is to find maximum bending stress. So use bending or flexural equation m by I is equal to sigma by y. Sigma max is equal to m by I into y. So our m is 24 multiply by y is this distance 101.39 mm. And I is So calculate this moment of inertia term again, because there is something wrong in this calculation. Calculate it again. 150 minus 101.39 square multiply by 5000 plus, here plus sign. When calculation I type here multiply sign, that's why answer comes wrong. Plus, that means I is equal to 11814660.5. So right here 11814660.5 plus 100 into 50 cube by 12 is 1041 666.66 plus this term 1181 46 60.5. That means this total, this much calculation is this 12.86 into 10 raised to 6. Now plus this term 101.39 minus 62.5 square of this term multiplied by 6250 is 945270.63 and 50 into 125 cube divided by 12 plus this term 945270.63. That means 17.59 into 10 raised to 6. So correct moment of inertia is 12.86 plus 17.59. That means 30.45 into 10 raised to 6. Why our last calculation of moment of inertia wrong? Because here while in calculator I put multiply sign. This is positive sign. Correct moment of inertia is 30.45 into 10 raised to 6. So now calculate 30.45 into 10 raised to 6. So sigma max, calculate maximum bending stress into see the cross section. So maximum bending stress is equal to 24 into 101.39 divided by 30.45 into 10 raised to 6 is, so here this 24 is in kilonewton meter. Convert this kilonewton meter 24 into Newton mm. That means 10 raised to 6 multiply 10 raised to 6. 24 into 10, this 10 raised to 6, 10 raised to 6 get cancelled. So only remaining term is 24 into 101.39 divided by 30.45. That means 79.91. 79.91. This 24 into 10 raised to 6 is Newton mm. And this y is also in mm. And this moment of inertia is mm raised to 4. So this mm cancel and mm raised to 2 remaining. So Newton per mm square is maximum bending stress. So maximum bending stress is 79.91 Newton per mm square. Thank you very much.